In this presentation, we're going to continue talking about object-oriented concepts, and this week we're going to talk about polymorphism. And before we get onto polymorphism, we're actually going to start by revisiting arrays. And if you remember, during the first week, we talked about static arrays, which are created of fixed length. That means we define exactly how many elements there are going to be before we run the program. But this week, we're going to have a look at creating dynamic arrays, in which we can actually set the size of the array at runtime, meaning that we don't have to declare the size of the array before we run the program. And also this week, we're going to have a look at creating an array of objects, as well as arrays that can store both parent and child objects as well. And then next, we're going to talk about polymorphism and how that applies to our classes. And this week we're going to look at that in the context of inheritance through function overriding. If you remember, function overriding is where we have functions of the same name, both in the parent and in the child. And we're going to use the keyword virtual this week to ensure that objects of the child class call the function in the child class, and objects of the parent class call the function in the parent class. Okay, so we'll have a look at that a bit later. Next, we're going to have a look at dynamic casting, which is an alternative to static casting, which, if you remember, what's characteristic about static casting is that it won't perform compile time checking, whereas dynamic casting does. Okay, so dynamic casting will automatically check that we can cast from one data type to another. And then finally, we're going to have a look at the friend keyword, which can actually be used to grant access to members that are in the private and protected interface of a class. But this does actually nullify the object-oriented principle of encapsulation. So we'll discuss the advantages and disadvantages of using this keyword a bit later. And so let's start by talking about static arrays. And here we're going to talk about static arrays of objects. So if you see the word static, we refer to a fixed size array, which means we define the number of elements that the array is going to have at compile time, meaning before it compiles and is run by the user. And when we refer to dynamic arrays, that actually means a flexible size array, where we can actually set the array up so that the size of the array doesn't have to be specified at compile time. Instead, it can be specified at runtime when the user runs the application. They can actually decide in the moment how big the array needs to be, how many elements it needs to have. And so over the following slides, we're going to look at different examples of static and dynamic arrays, and also fixed size and flexible sized arrays. But we're going to start by looking at a static array, which is a fixed size and also stores objects. So let's have a look at the syntax of how to do that. And the syntax is the same as what we've seen before. So we have to declare what type of data we're going to store in the elements of the array, as we see here. Then we have to give the array a name, and then we also have to specify how many elements the array is going to hold, how many contiguous memory cells should be allocated. Of course, we write that as an integer placed between the subscript operators, the square brackets. So this is as we've seen before, but rather than specifying a primitive data type such as int, char, or bool, for our data type this time, in order to store objects, we would have to write the class name of which we want to store the objects of. And in this case, objects are actually going to be created automatically. So we don't actually have to declare the objects for each individual element, like we might have to declare the value for a primitive type. We'd actually have to specify all the different integer values. But declaring an array of objects of class type actually initializes those objects for us. So we don't actually have to state them. But instead, we will, of course, have to fill in the values for the data members of those objects, which we're going to do on the example in the next slide. And of course, to do this, we do actually require a default constructor. So remember the rules which we had a look at in the previous presentation when we looked at constructors. If we're going to explicitly define a non-default constructor, then we also need to explicitly define a default constructor. But if we don't explicitly define either, then the compiler will implicitly create a default constructor. Okay, so it's either or. We either don't specify a default constructor, or if we do specify a non-default constructor, we also have to specify the default constructor. And then finally, because the objects that are going to be instantiated within the array elements are static objects, which, remember, the word static has a slightly different meaning in the context of objects as it does to arrays. Because those objects will be static, the convention then is to use the dot operator to refer to their members. And remember that with arrays, we also have to be specific and write what position of the array, i.e. which object within the array, do we want to call the member for. And let's have a look at an example of how to create a static array of objects. And so here, the first class we see is the GameObject class, which you'll notice everything actually resides within the public interface. We've got the integer ID, which may typically reside within a private interface, but here we've made it public, so we've got access to it. We'll see that in a moment. And then importantly, we've got an explicit default constructor and an explicit non-default constructor, which here just takes in the parameter ID and then assigns that to the ID data member. And then underneath that, we've got a display function which just prints the ID to screen. Okay, so that's the GameObject class, of which we're going to create an array within the main function of GameObject type. All right, so that first line, you'll see the data type there is specified as GameObject, and then the name of the array is objArray, and then you'll notice it's a fixed length array. It's a static array of 3 elements, where we place 3 within the subscript operators, the square brackets. Okay, so we've got a static fixed length array of 3 elements. And the first for loop underneath that is where we loop through each of those 3 elements, starting at 0. You'll see the loop counter there, int n, starts at 0, and then refers to the 0th element, which is the first element of the array. And then notice there, within the loop, we say dot ID. We use the dot operator to refer to the ID member of that particular element, of which is an object. And then we actually assign it the value of the loop counter, which will be 0 for the 0th element, and then 1 for the second element, and then 2 for the third element. And then in the loop underneath that, we do the same process, but we call the display function, printing out the ID for each of those elements, referring to the objects. Okay, so here we've got an example of a static array, which is fixed length, but has static objects, which also are anonymous. We don't actually know the names of these objects. We're not given that. We're not specifying the names of those objects. And so there we go. We've got an example here of a static fixed length array, which stores anonymous objects. And now, in contrast, let's have a look at creating dynamically sized arrays, which we don't have to specify a fixed length for when we define the array. So here we're actually going to be allocating memory dynamically. Therefore, this is more suited to storing the array on the heap, which, if you remember, that's what the keyword new does when we created our dynamic objects. We asked the compiler to get some memory from the heap to create the object, and then we set up a pointer to point towards that memory address on the heap. And we're going to do a similar thing here with creating a dynamic array. Here you'll notice that we are creating a pointer, as we did with creating a pointer to an object. And we're also going to use the keyword new, and then rather than calling the constructor, which is what we would have done for creating a dynamic object, here we're actually going to write the class type again, and then followed by the square brackets and then a value for the size of the array. So it's still going to require a size. It just doesn't have to know it at compile time. It's comfortable with this being a placeholder to then being received at runtime, where the user can type in a value for this size, and that's then placed in those square brackets there, the subscript operator, so that the compiler can then allocate memory on the heap for that number of elements. And here, in this case, the objects are still going to be instantiated automatically. And of course, it does require a default constructor like last time. And again, you'll notice that we're going to use the dot operator. So it would appear that we're still automatically instantiating static objects for the elements of this array, but we just get to dynamically assign how many elements and therefore how many objects there will be for this array at runtime. Let's have a look at an example to see how this works. And so if we have a look at an example of this, here in the blue box, we see a class called group. And if we have a look at the private interface, we'll see that we've got a pointer of GameObjectType, which was the class which we saw on the previous slide. And the actual pointer name is called objects. And you'll notice that we've also got a size data member, which we're going to use to indicate how many elements we want to allocate. So it's going to be a fixed size array within that context, but we're just going to allocate it at runtime. So it's dynamic in that sense. And you'll see that being applied in the non-default constructor here, where we're actually setting up a new address on the heap, setting up this new, you could say, fixed size array just on the heap, where we're saying objects equals new game object. So there's the reference to the class type again. And there is the square brackets with the size data member inside it, okay, which is going to be passed into this non-default constructor and then referred to there. Okay, and notice this is also a non-default constructor. So as this is defined explicitly, it would probably be a good idea to also define explicitly a default constructor as well. Perhaps that's just omitted for the purpose of this example, but just to follow the rules, if you code this up, just make sure that you include that. And then underneath this array allocation, we've got a for loop, which just assigns, again, the IDs. It assigns the value of the loop counter for those IDs. So that was the same as the previous example we looked at. Okay, so we've got here an example of a fixed size array being created on the heap, but the size of this array is just allocated dynamically. It's allocated by the user each time they run the program. So let's move on now and talk about creating a fixed size array that stores pointers to objects rather than objects themselves. So when we come to create the array, we're still going to have a fixed size where we'd write the integer value in between the square brackets, as we see, but we're actually going to have to set the array up to be of type class pointer rather than just class. Okay, that will become clear in the example when we have a look at that. And unlike the previous examples where the objects have been instantiated automatically within a fixed size array, here, because we're going to be pointing to objects, we actually have to create the objects ourselves. And so here you'll notice that we've got an example where we're going to be referring to a particular index, a particular position in the array, and then we're going to create a dynamic object by using the keyword new and then calling the constructor for that class. So this is a typical statement that you'll see for creating a dynamic object at each array element. And of course, as we're working with dynamic objects this time, we're going to use the dereference operator. So here in the third green box, we'll see rather than using the dot operator after we've referred to the particular position in the array, the particular index, rather than the dot operator, we're going to have the dereference operator to refer to a particular member, whether that's a data member or a member function. Okay, and in some instances, we may not even require a default constructor. We may actually be able to just refer to a non-default constructor. So let's have a look at an example. And so here in this example, we see that we're still referring to the class group. And in the private interface, we're going to create a fixed size array. You notice there it's of 3 elements. And those elements are going to store pointers to game object objects. And if you look at the default constructor in the public interface, you'll notice that in a for loop, where we loop through each element of the array from 0 to 2, for each element, we're going to create a dynamic object on the heap where we write the keyword new to create a dynamic object, and then we call the constructor for GameObject, and then pass n to it. I assume that's the ID being passed into the GameObject constructor. And so that's going to create a dynamic object on the heap, and therefore our array elements store the pointers to those objects on the heap. And then finally, in the display function, we're then just dereferencing the display function for each of those dynamic objects. Therefore, we should see the IDs printed to the screen. Okay, so this is an example of a fixed sized array which stores pointers to objects rather than the objects themselves. And then in contrast to creating a static fixed size array of pointers to objects, we're now going to have a look at creating a dynamic array of pointers to objects. And if you remember, back to the slide where we had a look at creating a dynamic array stored on the heap, if you remember, that was actually an example of a fixed size array where the size does have to be allocated just at runtime, but that array is going to be located on the heap. So therefore, we had to set up a pointer to point towards that array which stored objects. But here, in this case, we actually want to create an array on the heap which holds pointers to objects. So therefore, we have to put those two pointers together to create a pointer to a pointer. We actually have to create a pointer to point towards the array on the heap, which holds pointers to point towards objects. So therefore, that's two pointers, put them together, that creates two asterisks, a pointer to a pointer. That's what you have to include when you're declaring your type, so that's your class name, followed by the array identifier. And then like last time, each element is a pointer. So here we have to allocate the memory dynamically again on the heap. And then rather than type, we actually have to say type pointer. So that would be the class name pointer. And then the fixed size, whatever that is, going to be allocated at runtime. And also, like last time, each index has to be dynamically assigned an object of class type. So when you refer to the individual elements, which are the pointers to the dynamic objects, we need to create a dynamic object on the heap. So we do that via the keyword new and then calling the constructor. And then the array element stores the pointer to that object. But again, here we want to point towards that array, which holds the pointers to those objects. So that's why it's a pointer to a pointer. And so here's an example of this, where you'll notice we're working with the same classes that we were previously, the class group and GameObject class. And in the private interface of the group class here, we're setting up our pointer to a pointer. And because we want to create this array on the heap so that we can then allocate the size for which at runtime, we're going to have a pointer to that array on the heap. So that's our first pointer. And because the array on the heap stores pointers to other game objects, in this case, other objects more generally, it's therefore going to be a pointer to a pointer. Okay? And then in the constructor here, the non-default constructor, we are going to be setting up that array on the heap. As we see here, we're using the keyword new and then allocating the size for which it's going to be passed into this non-default constructor at runtime. And that's going to be set up on the heap. But remember, it's going to be of class pointers rather than the class type. So remember here, that's going to be GameObject pointer. You notice the asterisk in between the GameObject class name and the size. And then in the for loop underneath that, in the non-default constructor, we're going to be creating dynamic objects for each element of the array, looping through each element, of course. And so our array, created dynamically on the heap, is going to store pointers to those objects also located on the heap. And then finally, in the display function, of course, we just dereference the display member function for each of those game objects so that we can see those IDs printed to the screen. Okay, so it's quite an abstract concept, a pointer to a pointer, but just apply the same logic. If you remember that a single pointer is just a variable that points towards another memory address, you therefore just add a pointer onto that so that it's a memory address that points towards a pointer, which points towards a memory address. And just before we move on from talking about arrays, here we've actually set up an inheritance hierarchy where we're sticking with the GameObject class and the group class, but here we've actually created some children classes, which are player and NPC, which I believe in gaming terminology stands for non-playable character. And these classes inherit from the GameObject parent class. So here in the private interface of the group class, we're actually creating another pointer to a pointer. So it's going to be a dynamic array located on the heap, which stores pointers to objects of this inheritance hierarchy. And notice there that we've actually created it of GameObject type, which is the parent. And this is really important because this then allows us to store objects of the child type, or more specifically, point towards objects of the child type within the array. Because this doesn't actually work the other way around. If we tried to create the array of child type, of child class, then we'd only be able to store objects of that child type within the array, or point towards it if it's a dynamic array. We can't actually store other child types that are on the same level of the hierarchy, or indeed the level above, which is the parent type, because of these are technically all of different structure. And the inheritance hierarchy is only one way. It only works from the parent down to the child. It's the child that inherits from the parent, not the other way around. So just remember that if you want to create your array to store objects of the inheritance hierarchy, just remember that you have to create it of parent type rather than child type. And here, you may remember that in a previous presentation, when we first had a look at creating static 2D arrays, we said we'd come on and have a look at the syntax for creating dynamic 2D arrays. Well, here we are, we've arrived. And you'll notice here that we're going to be using a pointer to a pointer again. So that syntax is the same as the previous slides. But the only difference here is that each element of what would actually be set up as a single dimension array, a 1D array, to make it a 2D array, we actually have to create an array dynamically at each one of the elements. So that each element essentially creates an array, which in turn translates to the columns for that particular row in the 2D table or spreadsheet, whatever analogy you want to refer to there. It's because remember, 2D arrays are enacting a row and column matrix. So that's the difference here. All right. So what we actually see in the syntax, if we have a look at the blue box, is that we've got the pointer to a pointer. In this case, it's of primitive type. It's going to be storing integers on the array, on the heap. And if you have a look at the for loop, we see that we've got the myArray element, which you notice there, it's just a single dimension. It's just one value within a square bracket. And then we assign it a whole brand new array created on the heap using the keyword new, and then that size constant, which is just 10 this time, to create a 10 by 10 grid or table, matrix, spreadsheet, whatever term you want to call it, okay? So that when we refer to the array subsequently, we can add on another pair of square brackets. As you'll see in the very last line, we refer to the row, which is 0, and then the column, which is 0, and then give that the value of 53. Okay, so we've talked at length about arrays now, covered lots of different configurations. Some of those concepts are quite abstract, so if you need to listen to this again, please do go back and re-listen to it. But now we're going to move on and talk about polymorphism. And the word polymorphism actually breaks down into poly, meaning many, and morph, meaning forms or shapes. So something that has many forms or many shapes. And we had a look at this in the context of function overloading in a previous presentation, where we have functions of the same name, but just have different parameter lists and different return types. And now we're going to apply this concept of polymorphism to an inheritance hierarchy, where we have parent classes and child classes that both contain the function of the same name and signature, so that they exist in different classes. So it's exactly the same function, signature, but in both the parent and in the child class. But the default behavior in C++ is that function invocations are statically bound. And when you think back to our static arrays, that meant we had a fixed length of the array. We had to specify exactly how many elements were going to be in this array. Before compile time, we had to write it into our code, didn't we? So this takes on a similar meaning in that the invocation of the function is actually matched to the corresponding place where it's called. And in a future presentation, we're going to have a look at function pointers and how they're loaded up on the stack. But in contrast, dynamic binding allows you to match the invocation to a function at runtime. So again, this takes on a similar meaning to dynamic arrays, where we could actually specify the number of elements at runtime. So in order to allow for this dynamic binding, we have to use the keyword virtual when we declare our functions. And you'll typically see this being applied to the signature of the parent class function. So if you've got the same function in both parent and child, you'll see the keyword virtual being applied just to the parent function. And there's a reason for this in the function in the parent class. And the reason for this is that if you were to set up a pointer of parent type and then get it to point towards a child object declared on the heap, this then allows us to call the child function even though we started with a pointer of parent type. It actually overrides the parent's function of the same name, which could have been called had the pointer pointed to a parent object. But of course, as we're actually setting up to point to a child object, this allows us to then override the parent's function, which would have typically been called with a invocation to the child's function. Okay, so think back to the array, which allowed us to store both parent objects and child objects in. Because we set the array up of parent type, this then allowed us to store child objects as well as parent objects. And it's the same process here, where if you have a pointer of parent type, you can get it to point towards parent objects as well as child objects. So if you've got many children and you don't want to declare pointers to all of them specifically, you can just declare pointers of parent type and then point to the respective child objects. And by using the keyword virtual, you then ensure, in short, that you'll call the child functions rather than the parent functions. And of course, this is only in the event of declaring pointers of parent type pointing to objects of child type. If you're using pointers of parent type and pointing to objects of parent type, this is of course going to call the function in the parent rather than in the child. There's no downwards compatibility. And likewise with the child, if you've got a pointer of child type and it points to an object, then it will of course call the child function. Let's have a look at an example of this. This hopefully will help illustrate the point. And here in this example, we've got two classes. We've got a class for model at the top, which acts as the parent class. As you'll see below in the car class, you'll see the inheritance code there. We see the colon and then public inheritance, and then specifying the parent, which is model, of which it inherits from. But if you have a look at the functions in both of these classes, we've got the same function, which is draw. It's got the same signature. It takes no parameters, and it's also got the return type of void. That is identical in both functions, but the only difference is in the implementation of the function, because in the parent class, the model, we actually just print out that we're drawing a model. And in the child class, the car class, we print out that we're drawing a car. So the actual implementation is specific to each class, but the function itself is the same. It's an example of polymorphism. We got the same function, just in different places. So let's have a look at the main function now, and you'll see that in the first line, we're creating a pointer of parent type, model, and that's pointing to an object being created of model. So that's a parent pointer pointing to a parent object. And then underneath that, we've got a pointer of the child pointing to an object of the child. So we'd expect to see the respective functions being called. The parent's object should call the parent's function, and likewise the child's object should call the child's function. And you'll see there model points to draw, dereference operator, which we see draw model printed to the screen on the left hand side, and then underneath that car point to draw again calls the draw function for the child, which prints out draw car. Okay, so that's all fine. We've got the matching types of pointers to objects, so we expect to see, and indeed we see the respective functions being called for the class. But now, if we have a look at this example, notice how we've actually amended the draw function in the parent. Notice there we've added the keyword virtual in front of the return type. And if we go down to the main function now, notice that in the first line, we've actually created a pointer of parent type. Notice there, parent class model, and then asterisk model is the variable name, the pointer variable name. And then we're assigning it the address of a new child object, a new car object being created on the heap. That's where we have a parent pointer pointing to a child object. So which function is going to be called? As we've added the keyword virtual, we're enacting a dynamic binding, meaning that this is actually worked out at runtime. And this also allows us to call the child's function because we're pointing towards an object of child type, even though the pointer itself was declared of parent type, of model. Okay, so notice now that model pointing towards draw actually prints out draw car, which is the child's function. And then likewise, we also retained the child pointer pointing towards a child object, which of course there's no conflict there. So that will call the child's function as well. So this enacts the polymorphic behavior where we can declare parent pointers but then assign child objects and then call the functions that are specific to the object, the child objects, rather than the parent class. But beware, of course, this doesn't actually work the other way around because, of course, the child inherits from the parent, so we can't create child pointers and then point towards parent objects because the parent doesn't inherit from the child, so there's no two-way relationship. It's only one way. It's only from the parent to the child. So therefore, we have to create the pointers of generic type so that we can store child information in them. And if the parent's function wasn't declared to be virtual, we'd actually call the parent's function there because we set up the pointer of parent type, so it's going to automatically refer to the parent's information first because the type structure is of parent. So therefore, it would point towards the parent's draw function. So we'd actually see draw model there if we didn't include the keyword virtual. But because we do, we actually then dynamically bind the function, meaning that we can then invoke the child's function because that's the object. We want to point towards the child's information, the child's data members and member functions. And if we want to know more about how the compiler works out which function to call, we can have a look at the virtual function table, or as it's more commonly known, the VTable. And VTables are going to be generated for each class that has virtual functions or is derived from a class that has virtual functions. So every one of those classes will have an associated VTable, which is a static array that's populated at compile time. And each element of the array contains a pointer, a function pointer, to the virtual function that objects of the class can invoke. And it so happens that this is a hidden pointer, so we don't actually see it in the code. It's not written explicitly, but in the next slide, we're going to actually illustrate it so that you can see this and what it looks like. And it's just a pointer which points to the VTable for the base or subclass, depending on which one of them is going to be instantiated. So each class, whether it's a child class or a parent class, will have a VTable pointer. And so if we have a look at this slide here, note that this is actually at compile time. So we haven't run the program yet. We haven't actually got the main function here. This is just going to compile the classes as they're given. And you'll see here that we've explicitly defined the VTable pointer, which is the first line in all of the classes here. So notice there, the type is VTable, and then the pointer, it's actually *_ VPTR. So I think you'll find that's a keyword in C++. All right, so this is going to be hidden, but we've just illustrated it here explicitly so that we can see it. So that allows us access to the VTable for that class. And so let's have a look at the classes then. Remember, this is at compile time. And first class we see is the model class, which has two functions. They happen to be virtual functions. One is update and another is draw. So if we have a look at the corresponding VTable for model, the parent class on the right-hand side, notice there that we've got model update and model draw. So we've got the pointers to those functions, which happen to be virtual functions. Now let's go down and have a look at the car class, which inherits from model. So therefore car is the child. And as model has virtual functions, we therefore have a virtual function pointer in the child class here, so we can get access to it. And the child class is going to override the parent's draw function. So in the VTable, we see the pointer to the child's overridden function. Notice there we see car, scope resolution operator, draw. So we refer to the child's one. It's set up ready for us. But as we're not going to be overriding the update function, we've got a pointer to the parent's update function. Notice there model update rather than car update, because we're not specifying an overridden version of it in the child. Okay, so then let's go on and have a look at the final class, which is plain. Again, that inherits from model. And of course, as it's inheriting from a class that has virtual functions, we have a virtual table pointer, which is the same again. And here we are specifying overrides for both the update and draw functions. So therefore, in the corresponding VTable, we see the derived functions, the actual overridden functions. Okay, so the principle here is that the table only records the most derived functions accessible to each class. Okay, so you'll see the most relevant and specific derived functions here. Because, of course, we don't want to call the parents' versions of them. We want to call the function that's going to be specific for the class. If we've got overridden versions in the child, we want to call those overridden versions rather than the generic versions. Okay, so remember, this is compile time. If we go on and have a look at runtime, which is when we're going to invoke the code in main, this slide here is the example of runtime. So here's we're actually going to run the code and call the functions. So let's go through it line by line. And notice that we start by creating a static object of car. And then through that car object, we call update and draw. So therefore, we work with the car's VTable, which if we cast our eye back to the previous slide and have a look at the car VTable, notice there that we're inheriting the model's update because we're not specifying an overridden version of it, but we are overriding the draw function. So we therefore have the most derived function pointer in the car VTable. So we want to refer to the car's draw function, but we want to refer to the model's update function. It's back to the runtime now. Notice that the outputs that we see are indeed the parent's update function and the child's draw function. So that's good so far. Let's move on then and have a look at the next lines where we're actually creating a pointer of parent type, pointer of a model, which is called pModel, but we're going to assign it the address of the child object. Okay, so this is another example. We've got a parent pointer, but we're pointing towards a child object. So we want to really refer to the most derived versions. We want to refer to the child's information rather than the parent's, because the object is the child, it's not the parent. So therefore, because we're pointing to the child object, we can, and when we invoke the update and draw functions through that pointer, we refer to the car's VTable again. This enacts the child object, so we see the same things being printed. We've got the same functions. As we haven't updated the parent's model function, we're referring to that. But because we've got an overridden draw function in the child, we therefore call that rather than the parent's draw function. Okay, so hopefully you're seeing through this that the VTables are just the compiler's way of working out which functions to call. Okay, it actually plots out all of the different combinations and loads them up in the static array, ready for those functions to be called dynamically at runtime. And then finally, just before we move on from VTables, we're actually going to have a look at performance of algorithms and data structures in another module. That's C0658, which is all about data structures and algorithms and measuring the performance and how that varies depending on the size of the data structure and the efficiency, the number of steps involved with algorithms. But this is just a note here on this slide to say that invoking a virtual function is slower than invoking a non-virtual function. And the reason for that is that we require lots of additional steps in order to access this information dynamically, because we need a VTable pointer, which is the V pointer, is actually to acquire the virtual table for that given class. And then the table's got to be traversed. So the static array, we've got to go through each element in turn to access the correct function pointer to then invoke it. Okay, so we're going to look at arrays, as I say, in the next module, which typically, if we don't know which element we're referring to, we have to scan through them in a linear fashion. We've got to go step by step. So therefore, this is categorized as linear time, or in big O terminology, that's O of n. Okay, linear time. And n refers to the number of elements or number of nodes within a structure. So the bigger the structure, the more nodes and elements you have to iterate through step by step. So therefore, the time taken to traverse the structure is directly proportional to the size of the structure. It's going to take a lot longer to traverse through larger data structures than it is smaller data structures if our time is linear. Okay, so let's not major on this too much at this point. As I say, this is going to come up in the next module. For now, let's keep moving here with the presentation, and we're going to go on to talk about the keyword override. And the keyword override can be added to a function in the child class, which overrides the function in the parents class, to make that overriding explicit. Because of course, if we don't add the keyword override, as we haven't seen in all of the previous examples, that overriding behavior was just implicitly inferred. We didn't explicitly state it. So the override keyword is just a way to explicitly state that a function in the child class overrides a function in the parent class of the same name, of course. And the reason why stating this explicitly may be useful is that sometimes during maintenance, the parent class and child class can become out of sync. And this then prevents the implicit behavior being lost in case the function in the parent class is changed in some way. Maybe parameters are added or the return type is changed, or likewise in the child class as well, where the function in the child class may have amended parameters or amended return types. Therefore, stating this override behavior explicitly can avoid the later updates that may be made during maintenance. Just one thing to note is that if you write the keyword override in a function of the child class, but you don't have a virtual function in the parent class, then this is going to generate an error. Okay, so we've got to have a virtual function in the parent class if we're going to state that a child function is going to override it explicitly. And here, if we have a look at this example, we'll see that we've added that keyword override after the function name in the child class. Notice there that function update after the parentheses has the keyword override stated just before we open the braces. And as we've got the keyword virtual in the parents update function, this example is not going to generate an error. But of course, if we removed the keyword virtual from the parents update function, then this would generate an error. Okay, so this is just a way of explicitly stating that we want to invoke overriding behavior. Next, let's have a look at the keyword final, which if we apply this keyword to a function that exists in a parent class, but we have a child class which inherits from this parent class and attempts to override this function in the parent class, then adding the keyword final to the parent function actually prevents the child from overriding this parent function. Okay, so the keyword final actually prevents overriding in that context. And if you apply the keyword final to a class, that actually makes that class non-inheritable, meaning that other classes cannot inherit from this class declared final. And next, let's consider a different scenario where we want to access a function in the parent class explicitly through a child class function. So if we have a look here, we've got the class model, which is the parent, and then we've got the class car, which inherits from the parent model, and we've got a virtual function called draw in the parent, and we've got functions of the same name in both the parent and the child classes called draw, as we're used to seeing. In the parent class, it's declared virtual, meaning that it can be overridden by the child class's draw function. But note in the child class, we've got an explicit call to the parent's draw function, and that's stated through the scope resolution operator. So we can directly refer to the parent class model, and then colon, which is the scope resolution operator, and explicitly call that draw function, meaning that we would call the parents function as well as printing out the information specific to the child class, which is draw car. So we'd actually see draw model and then draw car. Right, so let's talk about upcasting now. And upcasting is actually a process that we've already been applying. Because if we have a look at the blue box here, notice that we've got a class for computer and then a class for laptop, which publicly inherits from computer. So we can deduce from this that laptop is the child class and computer is the parent class, as we're inheriting publicly from it. So when we come down to the main, we can create a pointer of the parent class, which is computer, and get it to point towards the address of a child object, which is laptop in this case, created on the heap. And this is possible because the child is a type of parent. It inherits the same structure, the same data members and member functions as the parent. So it essentially builds on the structure of the parent by adding its own member functions and data members, or maybe even overriding the data members of the parent. But that core structure of the parent is still within the child. So therefore, that's what makes this type of casting possible. And by referring to upcasting, we're actually referring to the UML diagram, where the parent is typically drawn above the child, and you see the inheritance arrow from the child pointing upwards towards the parent. So upcasting going from child, which is below the parent, to the parent, which is higher up in the diagram. But the reverse process of downcasting, going from the parent down to the child, is much more difficult because the parent doesn't inherit the structure of the child. It's only a one-way relationship. It's the child that inherits from the parent. So the parent doesn't actually know the structure of the child. Therefore, it doesn't actually share the structure of the child. So therefore, it makes it much harder to go from the parent structure to the child structure. So therefore, it's actually much harder to apply this process in the reverse order. For example, if we have a look at the blue box here, we've got the same arrangement of classes where computer is the parent and laptop is the child, which publicly inherits from the computer class, which is the parent. And notice here in the main function where we're creating a pointer of the child, but trying to assign it an address of a parent object. So as we said, that's much more difficult and doesn't work implicitly. So we actually have to resolve this explicitly, where we have to code in a process of resolving the conflict and migrating the structure of the parent to the structure of the child. So notice here, we've got a warning to say that this isn't going to compile this process because we haven't got an explicit conversion resolution method, which will actually sort out where the values for the data members of the parent go in the child, because of course those data members are not shared. The child only adds its data members. It doesn't actually have the parent's data members defined within the child. So it only inherits them from the parent. It doesn't actually define them within that class. So therefore, we've got to work out a place for those values of the parent, those shared attributes, maybe like ID or name or whatever types of details referring to the computer are going to go in the laptop, and also the member functions as well. So downcasting, in short, a lot more tricky than upcasting. So therefore, in light of what we've just discussed regarding upcasting and downcasting, it might be a good idea to employ dynamic casting when attempting to convert between child types and parent types. And dynamic casting, remember, differs from static casting, which we had a look at before. Remember, that doesn't employ compile time checking, but dynamic casting does employ compile time checking. So it will tell us whether it's safe to convert from one structure to another structure. And it returns the address of the object if it is safe to convert from one type to another, and it returns 0 if it's not safe. And we're going to have a look at an example of this in the next slide. But just before we do, notice here that the dynamic cast instruction has a similar format to static cast in that it's got the angle brackets, which might be indicative of a generic type or a template in C++. We're going to come to that, where we place the destination type that we want to cast to within. Where here, in this case, it's a car pointer in between the angle brackets. That implies that we want to be able to store a pointer to a object of car type or an address of car type. And within the parentheses here, outside of the angle brackets, is the type that we're casting from. So the from type, which in this case is an object. And so if we move on to this slide here, we've got an example of this where we've gone back to the game object and car classes. So if we see here, we've got the game object class at the top, and then the car class looks to be the child because it's publicly inheriting from game object. So again, we can deduce that game object is the parent and car is the child. And we've got a separate function that's outside of both classes here, which is called f. And here it takes in a address of a game object. Going to store it in obj. And then the first line of the function is where we attempt to perform a dynamic cast, where we attempt to cast the object which was passed in, the address to it, to a pointer of car type. So if we go down to the main function, first of all, we attempt to call f and then create a object of game object, which is the parent, pass that in, and then attempt to cast using dynamic cast. Notice that the output is invalid cast because we can't downcast from a parent to a child, or not at least in a simple way, because they have a very different structure, okay, like we mentioned in downcasting. However, if we have a look at the second line in main, that's where we create a car object and pass the address of it to the f function. So when we pass that to dynamic cast, that's a simple conversion, and that's a valid cast because they're of the same type. So if we have a look at the output, we see that valid cast is printed to screen there. So this is just an easy way that we can detect whether the casting can be performed safely or not. And it does this safely by returning 0 if the casting fails. So this is picked up in the if statement, which we didn't mention earlier, but hopefully you've noticed what's happening in terms of the if statement there. So if it detects the car object, if there's an object of car there, then we print out valid cast, but anything other than that, print out invalid cast. Okay, so in short, dynamic casting is a safe way to check whether you can convert from parent to child and child to parent. And now we've reached the final section of the presentation where we're going to talk about the friend keyword. And remember that the friend keyword allows access to data members or member functions that are declared private or protected within a class context, which wouldn't be available outside of that class, but declaring a member function or even another class to be a friend of this class will allow access to that private or protected information that's contained within a given class. So first of all, we're going to look at how we can make a function a friend of a class. And in the example, we're going to have a look at a external function, which isn't actually declared within a context of a class, but nevertheless, it is outside of the given class, which is weapon. In the example that we're going to have a look at. And we want to allow the external function access to the data that's contained within the weapon class. And it's got a private member called isMounted, which we want to gain access to. So therefore, we're going to define the prototype for that external function, define the signature with the return type and the function name and the parameters, if there are any. But crucially, before that, we're going to specify that this prototype, this function, is going to be a friend, so that the compiler knows when a matching function is called, the one that we've specified the identical prototype to, when that's being called, that's a friend of this class, so that it gains access to the private information, which is mounted in this case. So let's have a look at this then. So on this slide, we see the class weapon at the top, which has a private data member called isMounted, as we said. And then in the public interface, we have declared a duplicate of the prototype for the external function to the class, which you'll see below, which has got a complicated signature. It just unmounts the weapons, essentially. We won't go through all the code. But just to simplify it, we've declared that identical prototype, and we've declared that it's going to be a friend. So when we come down now to the external function, which doesn't exist within the context of a class, although it could do, we could also make that a friend if it was located within a class. We're going to have a look at classes in a bit, and we're going to have a look at how we can make an entire class a friend of another class. But this is just an external function that doesn't exist within a class, and notice now that we can legally gain access to the isMounted Boolean data member within this external function because we first declared it to be a friend of the class, which is weapon. So I'm not going to major on what this code does, but instead, hopefully this just illustrates that we can gain access to a private data member of a class that we wouldn't normally have access to if it wasn't a friend. And next, as I just mentioned, we're going to now have a look at how we can make an entire class a friend of another class. And so if we have a look at the green box here, notice that we've got a slightly different syntax. We're not actually going to create an object of the class, which we so typically would do, but instead we're just going to state which class. So we've got the keyword friend first, which is crucial, and then we've got the keyword class, which is the blue keyword class, just like we would have in the class declaration up above. And then only after that do we actually state the class name. Okay, so we're not creating an object of the class, we're actually stating the class name that we want to be a friend of this class. So if we have a look at the green box below, the second one, here's an example where within class A, we have declared that class B is to be a friend of class A. So therefore, class B has access to class A's private and protected members. So this will give you unrestricted access, basically, to everything within the class. In the previous example, we restricted the access to just one function, but here we're given entire access to the class. And here we apply that to the weapon example, which we saw earlier, where let's say that we now moved that unmounted function into the weapons manager class, which we haven't got an example of here, but let's just imagine that it's there. And now we want to do what we did before in the previous example, where that unmounted function has access to isMounted, the Boolean variable declared within weapon. To simplify things a bit and allow unrestricted access, we're just going to make the weapons manager class a friend of the weapon class so that the unmounted weapons function can have access to isMounted as it did before. Okay, so that's the syntax required for making classes or external functions friends of a given class. But just a note of caution is that, as you've seen, using the friend keyword actually nullifies the information hiding aspect, the encapsulation aspect, which is one of the core pillars of object-oriented programming. So the purists would argue that this is not a good design, and because it negates that core principle of encapsulation. They might argue that you might as well make everything public if you're going to allow access to the protected and private information. Why not just put everything in the public interface? Why bother at all having a private or protected interface? But some may counter that and say that, well, we're only allowing access to one friend class. We're still restricting access to every other class. It's still private and protected to classes that are not friends of this class. So it could be a sort of in-between approach to the purist OOP approach and a more relaxed approach, let's say. But the key thing here is thinking through the design of classes and ensuring that each class has access to the information that it needs to have. So it's always a good idea to be thinking about this, and possibly if you're making a lot of classes, friends, then that might suggest that you might need to rethink the design. If this information does need to be publicly accessible, then you might want to think about redesigning that class so other classes can gain access to it. Okay, but we'll leave that discussion there for now because we have actually reached the end of the presentation. So we'll stop here and transition to having a look at some of the exercises for this week. Great, so let's dive straight into the first exercise for this week. And in the first exercise, we're given a UML class diagram, which we have to implement, and then we're provided with some data that we need to pass to dynamic instances of objects created of this class. So first of all, let's set up the class structure. And here you'll see that vehicle, the class, is the parent for which the boat and car class inherit from. So first of all, let's create the vehicle class. Remember, we do this by going to the Add Class option in the Project menu. And let's set up Vehicle here. As this is the base class, we don't need to fill this in. So let's just create this here. There we go. And let's get to work with setting up the structure for the vehicle class. And remember to pay attention to the symbols that are provided here in the class diagram. Okay, remember that we said that this padlock here, hope you can see that, refers to private data members. And the key actually refers to protected. Remember, that's going to be public to the class hierarchy and then private to classes outside of the hierarchy. Yeah, and then data members or member functions without a symbol are public. Right, so let's set up, we're going to need all three here. We're going to need the private interface for damage. Set that up. Then we're going to need the protected interface for ID, which presumably our boat and car class will have access to and indeed have values for. We're going to get to that. And then the public interface is going to have a vehicle, which that's the constructor, of course. So let's set that up. We're provided with a non-default constructor, but might be a good idea to also have the default as well. Okay, and yeah, tell you what, actually, just to keep things simple and hopefully more viewable on this recording, I'm going to do most of the work within the header files this time, just to prevent having to switch back and forth from lots of different files, because we're going to have 3 different classes anyway. It just makes it easy on the recording. But of course, by all means, when you come to code this, if you want to, please continue working within the CPP file, the implementation file. But I say, just for the purposes of this recording, I think I'm going to do most of the work within the header file, just so we can keep the code together and reduce the amount of files that we need. So I'm going to set up a default constructor for the vehicle, because I'm pretty sure we'll need that later. And then the non-default constructor given here, per the requirements, we need a parameter list that has the ID and the damage integer parameters set up, which we're going to do that here. And then finally, we need a display function, which does what it says on the tin. It's just going to print things out to screen. So what we can do is we can set up the non-default constructor to assign the parameters to the data members. I'm going to use the keyword this just to avoid confusion. If you remember, we looked at this in a previous presentation where this takes on the reference of the current object. So any object of vehicle will be substituted with the keyword this, so that it refers to the data member, and then assign it the parameter. Okay, just because they got the same name. And for the display member functions, let's see, we're given an instruction here. It should display the name of the class and the object's ID to the console. So let's do that here. And we might also need to get, yes, I think we're going to have to include the relevant files, IOStream. Oops. And also using namespace std, so we don't have to keep referring to the standard library every time. And the name of the class is vehicle, and the ID is going to be the ID data member. I don't think we have to output damage at this stage. Let me just go back and have a look. No, there's no reference to damage, so we'll leave that for now. We'll probably come to it later. Right, so I think, maybe in the, in fact, we may not have to do much in the default constructor right now, so I'll leave it empty. I think it's mainly the non-default constructor that we're going to be using. So that should do for now in terms of the vehicle class, the base class / parent class. Hopefully we've got everything we need there. Let's now set up the children. So let's set up classes for the boat and the car class as seen here. So let's create a class for each. Let's create the boat class first of all. And in the base class category, remember to put vehicle there. So that it will set up the inheritance for us. It's not a major deal if you don't, by the way, because of course you can type this in manually. All it does is add this code here. Just makes it nice and easy for us. And then what have we got here? We haven't got any data members, but we have got a default constructor and a display. Okay, so we're going to see an example here of overriding, where we're probably going to want to call the display member functions in the children rather than the parent. So let's set up, these are going to be in the public interface, and we're going to set up the boat non-default constructor, int id and int damage. Again, so similar parameter list to the vehicle non-default constructor. And let's just check actually, because I think, yeah, we need to actually pass the information in the child, or as it's written here as the subclass, we're going to want to pass that to the superclass, the base class. And let's just check. Yeah, so here we're going to want to pass the data from the child to the parent. So remember, we can actually have an explicit call to the constructor of the parent by calling it here in the initializer list, the member initializer list. So if you have the colon there after the constructor parameters for the child, that is, you can then call the constructor explicitly, passing the values that need to be passed. And as it's of the same parameter list, we can write ID and damage there, right? So that those parameters which are passed into the child's constructor can be passed to the parent's constructor. And I don't think we're actually going to need to do much in here, so we can probably leave that empty. And then in the display function, we're presumably going to write something that's specific to the child. And oh yes, actually we're going to be writing out, rather than vehicle ID, which of course refers to the parent, we're going to want to write the child ID. So we're going to want to have a reference to boat in this particular case, and then print out the ID of boat. And is that all? Yeah, because again, we get access to ID through inheriting it. Belongs to the vehicle, as you can see. Oh, I can't show you it, but hopefully you can see it there. I can't hover over it, but hopefully you can see it. That it belongs in the parent class. So we get access to it because we inherit it. Right, so that's the boat, and I think we're going to do something very similar in the car as well. Yeah, it looks to be the same format. So let's just set that up very quickly. And then have a go at creating the objects. So this is the car class, and it's going to be the same format there. Remember to put the vehicle class as the base class there, parent class. And as it should be the same. Tell you what, let's speed things up and just copy this public interface. Let's copy that. Oh, might need a default constructor as well. I think I'll add that in. That can stay, that can be just changed to car there, and then this can just be changed to that. Yeah, and I tell you what we'll do is we will create default constructors for them. Again, even if they don't do anything, that might still be a requirement. So I'm just going to tidy up here, and then back to the boat class, oops, and create the default, an empty default constructor. Right, so I think we should hopefully have everything that we need. So now let's go to the main. There it is. And what we're going to need to include references to the children. So that's going to be boat and car. And then remember that they have references, they include a reference to the vehicle.h, so we should be able to get access to it through there. And we are going to want to now create the dynamic instances of each class and pass the data here. So remember, dynamic instance, dynamic objects. We're going to write the name, class name, and we're going to want to create a pointer set up to point towards a new object to be created on the heap. So remember, we need to call the constructor explicitly, and that object is going to be placed on the heap, which we then want to create a pointer that points towards that object's address. And as it's the non-default constructor we want to call, we want to pass this data, which so happens to be the ID of 1 and damage of 30. All right, and then again, same format for the boat object as the identifier B1 according to this. Call the boat non-default constructor, which has 2 as an ID and 50 as damage. And then finally, car, same format again, is going to have an ID of 3 and then a damage rating of 40. Okay, so hopefully if all goes well, we should be able to send the data that's passed through to the child constructors straight through to the ID data member in the parent. And then if we now attempt to actually call the display functions on these, let's see if we see them printed to screen. Oops. Okay, and let's give this a run. Hooray, and there we go. Notice that we see the matching data to what we put in, which is good. So it shows that we've successfully been able to pass that ID and the damage, even though we haven't printed out to screen, to the vehicle's ID data member. Okay, good. That's good. So now let's have a look at exercise 2, where we are instructed to modify the display member functions of the boat and the car so that they invoke the parent's display member function. All right, so let's go back to our children. Here we go. Here's the display member function. And remember that we can have an explicit call through to the parent's member function. And remember, that's through the scope resolution operator. So I'll tell you what, let's put it underneath here. And I'm going to refer to the vehicle class, and then notice that after the scope resolution operator, the 2 colons, we can call the display function. All right, and that will be an explicit call through to the vehicle's display. So might have to change some of the formatting here. Shame really, because we would like to display the vehicle class name for the vehicle's display, but of course that's going to be printed out when we call it on the boat. So I think well, I suppose we can get away for now. What can we do? That's we could say something like boat. I tell you what, yeah, let's comment this out, and let's have a print out here to say boat. And then for when we call it on a vehicle object, it will say vehicle ID. And then when we call it for boat, we'll see boat vehicle ID. So I suppose a boat is technically a type of vehicle. Should we not have wanted that word vehicle, we would have to take that out here. But I suppose every time we call it on vehicle, we just see ID. So until we rejig this around further, let's leave it as it is for now. So let's do the same thing here. I say the formatting is not essential, it's just for neatness. So really the main point is that we want to be able to call the display function on the vehicle. So let's show you that. Maybe we can have a go at the formatting later. And let's just say this is the car. As long as we have something to distinguish and we know what it is, that's good. So now that we've added explicit calls to the parents member function display, let's now see. Actually, let's put this on the same line just so we know. Yeah. Let's try and run this again now. If we go back to here. Let's just say that's 1 and 2. Let's run it again. Hopefully now we should see the vehicle ID and then the boat vehicle ID and then the car vehicle ID. Oh, yeah, there we go. I should have put a space there, formatting. But the idea is, yes, that we do call the parents member function there, which is good. That's and if we just set it up with different formatting, hopefully we can get the specific names for each of the classes without having confusion there. So we'll work on that. We'll think of a way to get a reference to the vehicle being printed out in the display of the vehicle, but then not in the child. So let's add just spaces there for now. Okay, but what I think we'll do is we'll move on and just have a go at the third exercise here, and then let you guys have a go. So what we've got to do here, we have to comment out the code within main and the statements that invoked the vehicle's display member function from within the child classes. All right, so let's do that. And then we need to then create a static array of pointers that point to objects instantiated from the vehicle class. And the array should contain 5 elements, that each one being assigned to one of the objects below. And we see here is the list. So, right, so let's set up the static array. So that's going to be a fixed sized array. And it's going to be of 5 elements. So set it up here. So I'll have a little output. So this is going to be the, exercise 3. And let's just put some formatting there. And now let's set up a static array of pointers. So it's going to be a fixed size array, as we said. Better to create it of the parents class so that we can store objects of the children, because that's what we're going to have to put in here. So let's do this. Let's say it's going to be the vehicle array, or any other type of name you so wish. And it's going to store pointers. All right, so that's where we got the asterisk there. It's going to store pointers. And it's going to be 5 elements. So now what we can do is we can set up new objects at each array element. So if I now, if I spell it correctly, if I now say vehicle array element 0, I can now set up a new car object at that element. And it's going to have an ID of ID of 1 and then damage rating of 35. Let's do the same for the rest then. If we have vehicle array element 1, let's now set up new boat to 55. This next one is a parent. Vehicle array 2 equals new vehicle 3 and 30. And then what's next? Car. Vehicle array element 3. It's new car 4 and 25. What's next? Vehicle array 4. And we want to create a new boat. So let's do that. New boat. And it's going to be 5 and 65. Great. Okay, so we should now have set up unique objects. And the array stores the pointers to those objects on the heap. Great. So now what do we need to do? We need to create a loop to invoke the display member function for each of the elements, each of the objects, the pointers that we set up. So let's do that. Let's create a standard for loop. Some 5. We've got 5 elements, so therefore to repeat 5 times. And then within the loop, let's then, for every element, so I can use I within the index there. And we want to point towards the display member function for each one. All right, so let's give this a go. Let's see what we see. Aha, and notice there that we see vehicle ID being printed. And we actually see the question here as to why is that? Why are we outputting vehicle rather than the specific constructors for each one? Okay, well, remember that we have to make the parent's display member function virtual in order to be able to call the overridden function on the child. So if we now make the display function of the vehicle, the parent class, if we make that virtual and run it again, should now see explicit calls to the display functions on the children. And let's have a look. Actually, because I changed the formatting, sorry. Let's go back and amend this. Let's put it back to what it was before. Yeah, because we took out the call to the parents member function, didn't we? Yeah, so sorry, we do have all the code we need, we just need to call the right one. So now let's call it again, and we should see it nicely formatted now. And there we go. Now that we see the right class names being printed for each of the objects. Okay, so there we go. That's a good illustration there of overriding and polymorphic behavior. And I think actually that was the 4th exercise, yeah. So have a go at those, see how you get on there. And then once you've had a go and you've got it working correctly, have a go at the remaining exercises, which take it further. All right, so give it a go and see how you get on.